Hello everyone, I am excited to share you with our project that brings the realms of artificial intelligence and hardware solution. Our project name is Word Recognition using Neural Designer. Talking about the agenda that we will be carrying in our presentation would be these: introduction, process flow, selected hardware, MFCC samples, data set, neural network architecture, and at last, testing. As we know, word recognition is a fundamental aspect of many applications, including transcription, speech to text, and language processing. Our project centers around the utilization of a remarkable tool called Neural Designer. For those who are not familiar or say unaware about Neural Designer is a software designed for machine learning based on neural networks. It is a user-friendly app for data science and machine learning. It allows you to build AI-powered applications without coding or building block diagrams. However, our project goes a step further, entering the concept of hardware. Trying on the hardware serves as a bridge between the digital realm of Neural Designer and the physical world where real-time word recognition matters the most. Coming on to the process flow, these are some steps we used while making the project. Let's say, firstly we collected some data input, then applied some filtering to improve the data. Then we divided the speech data into frames, and then we extracted the MFCC values for each frame. Now, the second phase, that is, we moved into Neural Designer model configuration. We use the MFCC value as an input to design neural network. After some training data preparation, we move into hyperparameters, that is, the number of layers and neurons to get a good accuracy for the model created. After that, we deployed the resultant code. Moving forward, talking about the hardware we used to deploy our model on. We used a Raspberry Pi 3B and a MEMS digital microphone, that is, an application-specific integrated circuit, to record our audio. This is a sample of what a 1-second audio with sampling rate 22,100 would look like. There are 13 rows for MFCC which indicate different aspects of sound as floating points. And for 1 second, we have about 44 such rows. Now, coming up at the data set, or say the implementation of model, first of all, we recorded multiple audio files, each of 1 second, with a fixed sampling rate and named them words accordingly for each row. This would be our target. We merged all the above into a CSV and provided that file to our Neural Designer as training data. We have a total of 5,270 rows for this model. Talking about the data analysis. In respect of, as you can see, our data analysis is done in respect of histogram, input target, correlation, and box plot before training. In histogram, we can see the frequency of occurrences. In this input target correlations, all the inputs are positively correlated to our target. That is to say, if we can increase the input value, output will also increase. Here, the box plot represents the median, quartiles, and potential outliers in a concise manner. The Neural Designer divides the data in a ratio of 60-20-20 as training samples, selection samples, and testing samples respectively. Our data was already pre-cleaned, so we didn't exclude any sample. This is our ANN model architecture consisting multi-layer perceptron, where we can clearly see 3 layers. Firstly, we have a scaling layer. In the second perceptron layer, we have 22 neurons which receive scaled input with an activation function of sigmoid. As output layer, we have a probabilistic layer as we can use multi-class classification. If we had used an approximation model, it would have been an unscaling layer as output layer. Moving ahead with our training strategy, our loss index consists of mean square error and L2 regularization, which is a ridge regularization. Our optimization algorithm, that is LMA, or say Leavenworth-Marquardt, which is a second order algorithm. These are some snaps of how our Python code and expressions are generated. This is the confusion table, that is our testing part. Talking from the last column named as total, there we can see 263 as the total yes output. But our output predicted by our model is 280 as yes, 17 as no, and 28 as sure. These predicted no and sure are errors or say wrong predictions. And same goes with the no sure word predictions in the table. And all the 1054 testing samples have been predicted and computed to get this table. By seeing the error table, we get to know what would be the accuracy of our model by using different error functions, and as a result, mean square errors gives us the best possible accuracy. So we have used it in our final model. Now, as we can see after training of our model, these are some of our statistics which would help us to understand the functioning of our model, where we can see importance of each MFCC values as an input which decides the output. So now moving on to the code explanation part. Now there are two files we can see on our Raspberry Pi. One is a code generated by the neural designer. We will use it as a module and integrate it in our main code. This way we won't have to change anything in the code generated by the neural designer. Talking about our main code, firstly we can see all the libraries we have imported. I won't go in the specifics for now. Majorly talking, we will use the neural designer to compute our results, and Librosa is used to calculate the MFCC values. Here we have declared our MEMS microphone as our input device. In this part, we record the audio. Here we are analyzing the audio first. MFCC is created, then those MFCC values are passed onto the model in the function, that is nn.calculate outputs. Then after computing the outputs, we find the average probability for each word and display the corresponding strings with the highest probability. Moving to the last part, we aim to demonstrate a real-time output on the hardware. When my friend utters a specific word such as yes, no, and sure, the resultant output will be displayed on an LCD screen, providing a visual representation of the spoken words.
No, no, yes, no, sure, yes.